Hey, what's up, guys? So in this video, we're going to go over vector reflection. We're going to use vector reflection to create basically a bouncing laser in an FPS game. So I have this very basic FPS setup, and when I shoot, you'll notice that the laser will hit the wall and it will bounce off. So the idea is we're going to use vector reflection to essentially to get this effect. Um, and at some point, of course, it'll just like burst after, some defined number of bounces. Um, So first I'm going to basically go over the math and then afterwards we'll jump into the implementation. So I'll start by drawing out the surface here. And then I'm going to draw out a normal vector to the surface. And then of course we have our incoming projectile here, right? And then we're going to have our reflected, we're going to reflect it over the surface. We're going to have a reflected um, vector over here. Uh, and I'm going to do the best I can to label this stuff. So let's see, we have our n over here. We have our normal vector here. We're gonna have we're gonna have our reflected vector. We'll call this guy r, and then we have our direction vector d. We'll say direction. This is essentially the direction that the projectile is traveling in, and then it's gonna hit the surface and it's gonna bounce off and move into this r direction, this reflected direction. So basically, what we're trying to do is we're trying to find r, right? We don't know what r is. We're trying to figure out what r is. So if you recall, let's just quickly go over some basic vector arithmetic. So suppose I have some vector here, v, and some vector here. We'll call this u, right? So I have some v here, and I have some u down here. And if I wanted to add these vectors, the geometric representation can be found by using there's there's a triangle method, and there's also the parallelogram method. But essentially, what we can do is we can translate these vectors anywhere in space, right? All vector really is just a magnitude and a direction. There is no positional information regarding vector. There's no position origin associated to it. It's just again a magnitude and direction. So I can translate these vectors anywhere in space. I could bring u up here, right? And I bring v over here and sort of complete this parallelogram, and the summation of these vectors would be the vector that spanned from the base of v and ends at the meeting point, if you will, of this parallelogram spanned by the vector. So this would be v plus u. And just going over that, and you'll see why in a second. So let's say we're going to solve for r. Again, we can translate r anywhere in space, right? Because I can bring r over here, for example, right? I could bring r here, and this would essentially be this would be the same, vector, right? This is the same reflected vector because it has the same magnitude, it has the same direction, and I can translate it anywhere in space. And I can do the same with d. I can bring d down here like this. I can say, well, this is also d, right? Because it has the same direction and has the same magnitude. So, and if I was to look at r, right, I could see r as being essentially, um, I can represent r as basically, let's see here, r. I can represent r as d, minus some vector, and we can call this vector v. Let's say this is our v, right? We're just going to sort of draw a vector that's again similar to how we did v plus u, that's split right between this parallelogram, and we're going to say this is d minus v, and we'll see why in just a second. So we'll call this guy v, right? So d minus v can be also, I mean, we can also think of this as, typically when we subtract vectors, we can think of this as essentially just being d plus negative v, right? It's an easy way to think about it. It's just all you're doing is really flipping the sign. So if you flip the sign of a vector, all it really does is change the direction, right? So here's this vector that's traveling in this direction. And when we flip it, it's going to be going in the opposite direction. It's going to be going in this direction, up like this, right? So this is going to be our new, this is going to be negative v. And again, we have d down here, right? Oh, sorry. We have d traveling in this direction down here. Excuse the drawing. It's a little trying to get the straight lines here. So again, if we wanted to add D and V, right, we can use the same technique down here. What we would do is we would bring both the base of both of these vectors and you know line them up. So if I lined up D and I lined up V, right? If I translate V over here, basically, um, just draw this here so we know what we're looking at. Call this negative V, right? We have D down here, right? I would say, well, what is D plus negative V? Well, again, similar to how we had U and V over here, we can translate these vectors, parallel translate these vectors. I can bring V here, or negative V here, and I can bring D over here. And again, we would go from the base, extend out, right? Well, if you look here, I mean, this is just R, right? This is exactly that vector. This is the same vector that we're looking for. We're looking for R. So, I mean, R it will be D minus V, or D plus negative V. And now we have R. And again, we can translate R anywhere in space, right? We can bring it, you know, anywhere in space. So I move these vectors around, manipulate them in such a way that I can basically so I can basically solve R. Um, so all that's left now is we know D, right? We don't know R, because we still don't know what V is. Well, remember, V initially was the vector that went from here all the way down to here in this direction, right? So how can we bring D onto N? Well, we know we can use, you know, we can use vector projection. We can project D onto N so that we can get a vector that spans from here, right? Spans from here all the way down this way, right? We can call this guy D prime. And then, you know, if we want to get this position here, well, this is just two times D prime. This is this vector scaled by two. This is, and then this would extend out all the way here, right? So basically what we want is, let me try and erase some of this stuff so I can work here. So let's get rid of some of this stuff here. Oops. So, okay, so we're trying to solve for D prime, right? So, well, D prime is just going to be, it's just going to be, um, you know, the projection, right? The projection of D onto normal vector, right? And the projection of, you know, the projection formula of projection D onto N is just going to be N dot D, sorry, N dot D, right? All over the magnitude, or rather N dot N, which is going to be the magnitude of N squared, multiplied by N, right? This will give us a scalar, and then we multiply a scalar by a vector, we'll get a vector. So, and just to show you why we can use a dot product in the denominator, well, the dot product of two vectors here, right? If I was to say the dot product of two input vectors, and let's just call them V for now, right, is basically just going to be the magnitude of V multiplied by the magnitude of V times the cosine of theta, right? This is the formula for a dot product. If I dot, if I was to dot two different vectors, it would just be, you know, the vector V and U, for example. That actually looks like a U. V and U, for example, the magnitude of V times magnitude of U times the cosine of the angle between those two vectors. Now, if my input vector is the same, then really this just ends up being the magnitude of V times magnitude of V times the cosine of the angle between the two vectors. But because the two vectors are the same, the angle between them is just 0 degrees. And if you go back to, you know, a unit circle, right, the cosine of 0 degrees, right, the x component of 0 is 1, right? This is just 1. So essentially what we're left with is just, you know, the magnitude of V times magnitude of V times 1, which is just going to be the magnitude of V squared. And that's sort of why we can this is sort of why we can dot the product, or dot the vector rather, by itself, and that would give us the magnitude of the vector squared. All right, so let's jump into Unity, and so I have these two scripts here. One is obviously the bouncing script, and the other one is just a basic projectile script. So I'm going to update a prefab I have. Going to remove the projectile laser, and I'm going to add this basic projectile script, and I'll sort of go over what the script is doing. So it's going to be our impact prefab. So if I now play the game, I will end up with a laser that hits a wall and basically just explodes, doesn't bounce. So this is the script here. We'll go over the script real quick. So I have this float speed variable, so just controls the speed of the projectile. I have an impact prefab, and I have a move direction here that's essentially moving in the direction that transforms forward. And then when we trigger collision, we're just going to get the get contacts, returns an array of contact points. So we're going to use the first contact point, and we're essentially just going to instantiate the prefab there, and we're going to give it the identity matrix for the rotation, and then we're going to destroy this current game object, and this is going to be moving, and then we're just going to move the projectile based on the position, direction, and then of course the speed by the delta time. Um, so now what we want to do essentially is we want to be able to say, hey, we don't want to actually, burst when we collide. We want to be able to bounce. So we're going to introduce a variable. We'll call it num bounces. And this is essentially just going to be how many times we will bounce before we actually generate the impact prefab. And then when we collide, right, we're going to check if num bounces, if we're decrement num bounces, pre-decrement num bounces. We're going to say if this is 0, less than or equal to 0, then we want to do essentially all this guy over here. We want to instantiate the prefab, and we're going to destroy the object. Otherwise, we are going to, right? Otherwise, we're going to bounce. So remember, if we refer back to the formula here, right? We want to get the projection of n onto d, and then we're going to scale it by 2 and subtract d from there. So first, we want to get the surface normal. So we can just say, normal is equal to contact normal. And then we want to project. So we want to do a projection. So we're going to say vector3, the projected vector, or the projection vector, right, is just going to be, the dot product. I'll say 2. We're going to multiply by 2. So 2 times, if I can type here, the dot product, right, between the normal, right, n, and our direction vector. Well, our move direction is the direction we're traveling in, right? And then we're going to multiply that all by the normal to get a vector back. Now, previously we were dividing out the magnitude of the normal squared, or the surface normal. But I mean, if it's a normalized vector, then you really don't need to do that, because the length of that vector is just going to be 1. So multiplying the length of it squared is just going to be division by 1. So you can sort of get rid of the denominator altogether, and you're just left with the dot product times the actual vector. And then we're going to reassign move direction to be equal to, right, d minus, again, 2 times the projection. And we're done. That's it. And then, we gotta go back here. Let's say num bounces is 3. If we play it, we should see projectile bouncing. You'll see that the rotation is a little messed up. So that's because we're not actually updating. So what we want to do here is we want to say transform.rotation is equal to quaternion dot look rotation. So this is going to take a forward direction, and our forward direction is going to just be our move direction, and then our upward vector is just going to be it's just going to be the y up. So we could just say vector3 up, which will be 0, 1, 0, and then we should be able to get. There you go. Lasers are moving, bouncing, and updating your rotation. That's it. Very simple. Yeah, and you guys can use reflection for a lot of other cool cool things. So yeah, thanks for watching.